we have already quite jumped into the digital twin field, so I decided to switch the order so that you can have a more clear view first on the of our work at Warwick. So this part of work, we aim to address the issues related with sparse sensors. So we only have sparse scatter sensor in the real world farm. Even for a single wind turbine, it's very hard to know the clear real-time picture of the flow field experienced by a certain wind turbine. The existing measurement technology is mainly consisting of, for example, SCADA data, which is point characterization of wind turbine at these single locations. And if we explore the LiDAR data, for example, this is an illustration of a 2 laser beam LiDAR, and the LiDAR can give you the line of sight measurement at these sparse scatter locations. And this poses 2 problems. The first one is they only give the line of sight wind speed, which is the wind speed vector projected into the laser beam direction. So the wind directional information is lost. So we do not know exactly with LiDAR measurement the wind speed, the wind direction, and the wind speed needs to be estimated in that case. And the most difficult issue is still the data is still at sparse scatter locations. And in order to build a digital twin of flow field, we actually want to reconstruct and predict the whole flow field relevant to the wind turbine. And this kind of approach very hard to be achieved by physical modeling approaches. The low fidelity models, they can be calibrated in real time, but this kind of approach already meets a lot of useful information in the flow field. And for the high fidelity CFD models, if we use 8, the high fidelity model with measurements, then it becomes very complicated. It takes, I don't think, like, it would take at least several weeks or several months to run a simulation to calibrate a CFD model with real-time feeding of data. So that's not possible, not even with the largest supercomputers in the world for this single task. It's not possible. And for the data-centric approaches, we talk about machine learning, and many applications is still in the area of supervised machine learning. Basically, for that kind of approach to work, we need a target. Then we train a machine learning model to mapping the input information to the output. Then after that, the machine learning model can be used. But in this scenario, the challenge is that we do not have a target. So we do not meet this target, but we want to know what's happening in the world. So this comes into our digital twin for the flow system for a single wind turbine, which is achieved by fusing data and physics in framework, physics-informed neural networks. So from the terminology of machine learning, this is unsupervised learning. But if we go into the detail of the model, the training loss function basically consisting of 2 parts. The first part, the L2 part, is actually supervised part. So it's the evaluation of this L2 requires the real-time LiDAR measurements, and the training aims to minimize the neural network output, the mean square error of the neural network output with LiDAR measurements. The important part is the physics-informed part, which basically incorporates the flow physics inside the machine learning model. And this here, the flow aerodynamics is described by Navier-Stokes equations, and the Navier-Stokes equation incorporated into the neural network for the training. So the training, during the training process, in order to train a machine learning model, we minimize the loss via a certain optimizer. So the most popular one is gradient-based, such as ADAM optimizer. And the optimization process simultaneously achieves the matching of the neural network output with real-time measurement, and at the same time make sure that the output is the flow field that satisfies this governing equation, which is Navier-Stokes equations. So again, we summarize that from the outside, if we treat the whole approach as a black box, then the training data required is LiDAR measurements output. So eventual prediction is the spatio-temporal flow field. So it's a whole flow field in real time. So this is the results for a single flow field in front of a single turbine. And this is a prediction. This is the ground truth. So this, because we currently test this with high fidelity simulations. So the simulation provides the experiment platform for method evaluation. And for this prediction, the machine learning model is trained only with this measurement at these locations marked as cross lines. So in total, we have, in this case, 22 measurement points, and each measurement represents the line of sight wind speed along the laser beam direction. This is the input for the machine learning model, and the output is this whole video. As we can see that it contains much rich information of the flow structures in front of this turbine. For example, this red dot, the wind speed goes from 6 to 10. The right part is the higher wind speed. So the red dot actually represents a gust in front of the turbine. We can see that the gust, the flow structure travels from upstream, then eventually hits the turbine. So this kind of flow information, you cannot obtain it with raw LiDAR measurements because it's only consisting of sparse scattered locations. And in most of user cases we've seen in the literature, the LiDAR data is usually used by just averaging these measurements, then just use this as a effective wind speed at a single average locations to provide information. But with this kind of digital twin approach, we can reconstruct the whole thing. So it can, and based on this rich information, we can extract other relevant information according to your user cases. For example, we can extract the instantaneous wind speed at different sections of these blade locations, and we find good agreement between the ground truth and our prediction. And also, for the control system, one may be interested in the effective wind speed at different distances in front of the turbines. So we can optimize kind of information as well, and we can see that the prediction match with the ground truth quite well. But still, this is a two-dimensional case. And we first evaluated the approach for a set of different cases in order to see how robust the approach is. The video I've shown in the previous slides is a baseline case. Then we've tested with by adding various levels of noise to the measurements and also reducing the resolution of LiDAR measurements and test different loop direction and also consider different inflow turbulence levels. And for all that kind of cases, the prediction error remains very small. And after that, we're confident that we want to extend this kind of approach to a full three-dimensional space because the actual turbine lives in this three-dimensional space as us. So in order to really to see the surroundings of this turbine, we've extended it with scanning LiDAR setup, and this is the results for the slice view in the XY plane and also XZ plane. This is the slice view in the XY plane, and this is the prediction results, and this is again the ground truth. We can see, for example, in this video that the flow structures is retrieved by the digital twin, and also the main flow features such as the wind shear. So the wind speed increase with the height is all captured here. And for the XY slice view in the XY plane, which is a plane parallel to the turbine rotors, this kind of information can be used to feed to the control system so that we can know the two-dimensional flow field in front of the turbine before the flow field arrives at the turbine location. And similarly, we can extract useful information, but in this case, we can already incorporate this movement of turbine blades so that we know we can extract the wind speed at the relative wind speed at each turbine blade sections from turbine blade root to the turbine blade tip. And we can see the both the oscillations due to the turbine rotation and also the irregular changes because of the intermittent incoming inflow. And we can also extract the effective wind speed at different distances to the turbine. And this is averaged in the span-wise direction, and we plot it with against the height, so that we can know that the wind speed actually increases with height. And this is the case for wind turbine operating in the 8 meter per second scenario. And we also tested it with all kind of different wind speed scenario, which is typical for wind turbines operating in below rated to above rated conditions. And for all that kind of cases, we are able to achieve good accuracy for all the cases. So that's for the flow field covering the inflow of single wind turbine. We then, because we are concerned with this aerodynamic inflow, we then move on to the wind farm level. For the wind farm level, the fusion of the physics and data we are presenting is further extended. Further information which is realistically available in the current industry. So aside of LiDAR data, we have in this system incorporate a further module which is to achieve the turbine modeling. And for the turbine modeling, we need some basic information such as the turbine location, turbine yaw angle, and also the rotor thrust in real time. This rotor thrust can either be measured if we have sensor in place, or we can estimate based on the power generation of the turbine. So this is the current results I will present. This is only 3 information from turbine side. And again, for the flow measurement, it's a LiDAR measurement, and for the physics part, aside of the novice flow applications, we also model the wind turbine rotor via the actuator disk representation of the turbine. So basically, we are also modeling the impact of the wind turbine rotor in operation on the flow field. And this leads to the first digital twin able to predict such in situ spatial temporal wind farm flow field, capturing the wake interactions between individual turbines. This is the first case study. We consider grid wind farm, which we call grid from the control perspective. Each turbine is operating in its own interest, so every turbine in this small farm operating towards the wind direction. And the top video is the digital twin prediction, and bottom video truth. And we can also see the scanning LiDAR configuration measuring the flow field. And we can clearly see the in extending from single turbine to wind farm, the main interest is actually the wake. So as long as we capture these wake effects, then basically the most difficult part is that we can see that the real-time behavior of the wakes is captured quite well by the digital twin. Can see it again. Okay. Because we want to know from this video that for conventional analytical models, most of people when dealing with LiDAR data doing wake modeling, usually we consider the static wake model, but here it's all dynamic. So we can clearly see the meandering, for example, the meandering of the wake. So when in wind turbine aerodynamics, the meandering of the wakes refers to the crosswind movement of the wake structure. Because we can see that if we consider this in average, we will see a structure like a very steady, and the wake will stay in the middle of this turbine and impacting the next turbine. But here it's all steady, it's all dynamic, so we can see the flow structure is meandering in this crosswind direction, and also it propagates from upstream to downstream. And we can see a very good corresponding match between the digital twin prediction and the ground truth. And based on this flow field, we can extract useful information as for single turbine cases. But here we can observe much more interesting information. For example, from the effective wind speed along this center line of this row of turbine. So this is for the first row, and this one is for the second row. We can clearly see that the incoming wind speed is around 10 meters per second. Then the first turbine is located here. We can see clearly due to the presence of the first turbine, the wind speed suddenly drops. This is the wake region characterized by the reduced wind speed. And the wind speed continues to drop at around below 6 meters per second. And this is actually the operating condition of the second turbine. Therefore, the second turbine actually operates in a very bad situation, generates much less energy, even though it's the same turbine as the first one. And then after the second one, we can see a small drop again, then slowly recovers. This is due to the enhanced mixing, because the wake region actually is characterized by not only the reduced wind speed, but also increased turbulence level. So whenever there's turbulence, the mixing is enhanced. So it encourages the change of energy between the wake region with the free stream wind. Therefore, we can see a slow recovery of the wind speed for the higher wind speed until it hits the third turbine, which is this one. The wind speed drops again. And the similar observation is same for the second row of turbines. And here this is the plot of the wake profiles at different locations from the free stream inflow to the first turbine, which is situated at the 0D location, then the second turbine 5D, the third turbine at 10D. And we can see the development of the wake profiles. For example, the free stream inflow, because we are trying to simulate the real-world simulation, the real-world conditions as realistically as possible. So there are turbulence in the inflow. So we can see it's not uniform, say, turbulence inflow until this 0D location, which is the first row of turbines. The first row of turbines, we can already see the wakes structure, so the reduced wind speed. Then the wake slowly develops until it's from a double peak. Double peak is because of the turbine has essentially in two-dimensional space. We can see that turbine has two blades. It is in three blades, but the mean induction is at this location here. Then due to mixing, it slowly recovers and evolves into a single peak structure. And if we consider traditional analytical wake models, this will, in most of the studies, people will model this kind of wake profile as Gaussian. But clearly, if we are doing real-time unsteady wake behaviors, it won't be Gaussian. It's much more chaotic. And we then move on to the second case study, which is a wind farm under the yaw control strategies, which is the yaw control trying to steer the wake away from downstream turbines, so that downstream turbines can operate in a much favorable condition. And again, we first draw the dilution predicted flow field and compare with ground truth. And due to the yaw angle of the front row wind turbines, we already seen here the wake is generated steered away from downstream turbines, so partially overlapping with the downstream turbines. And we can see a good comparison between these prediction with ground truth, including the deflection and also the meandering in the crosswind direction. And if we look at the effective wind speed, again, the inflow condition remains the same, is about 10 meters per second. Then after the first turbine, it drops to about below 8 meters per second. But if you remember, we can come back to have a look. So in the gradient farm, it actually already drops to around below 6 meters per second for the second turbine. So this is the reflection of the flow field capturing the strategy of yaw control is actually working. Then after the second row turbines, we can see that they are recovering of the wind speed. And also this can be seen more clearly if we see the wave profiles. So clearly the peak. So the center of the wave is there. For this row turbine, we can see that it's downward in this figure, and similar for the second row turbines. And in real-world scenarios, often some turbines will be stopped due to various reasons, either fault or maintenance. So we further consider a case where a graded wind farm, but with one turbine now stop working. And in that case, we can see a good prediction results compared with the ground truth. And again, if we look at the effective wind speed, this is for the first row, where the second turbine stop working. This is the second row, which is all three turbines operating. And we can clearly see that there's no turbine here, so no further reduction of the wind speed, but the wick generated by the front turbine is just propagating through and then impacting the final turbine. So we can see that the near wave region, the wind speed drops very fast. Then due to the enhanced mixing, the wind speed increases, and it's until the reach about 6 meters per second for the last row of turbines. So this is the digital part of work, and I will then move on to the modeling part before you have any questions.
I just have a question.
Yeah.
What is this Y?
Which one?
Y. What is your Y-axis?
This y-axis.
No, there.
This one.
Bottom.
This is because in wind turbine aerodynamics, people usually put this y in the y-axis and the velocity in the x-axis. It's just it's in convert, like most people in other fields will do the so the y is the crosswind coordinates as x-axis, but with the quantity of interest in the y-axis.
What is Y in physical terms?
Y is just this coordinate, the spatial coordinates.
The coordinates.
The coordinate of the space. The one. So it's just because this, for example, for this profile, this zero profile, it's actually the plot of the wind speed extracted along this line. And the y is the y coordinate is the Cartesian coordinate of this framework of this frame.
And what are those values then? All those.
Then this x-axis is actually the wind speed. So actually, if you look at it this way, it's more conventional.
I mean, this axis is different, right?
This axis is different. This is a two-dimensional space. This is the wind direction, the coordinate along the wind direction. This is the coordinate across the wind direction. And this y is the same. This y is the crosswind coordinate.
I think Y just the location.
It's a location.
Yeah. This is the
Yeah, it's just confusing. I think probably because of conventionally when we plot something, like if we want to plot the change of wind speed against a certain say y coordinate, then people will usually plot this kind of information as there's no fault here. So usually people will plot just a figure with x-axis as y and y-axis as u.
No, I was expecting that what you saw in the y-axis would be the velocity at that.
Yeah, this is velocity. Axis is velocity.
That's the velocity of the wind along the horizontal direction. And what is this in the y direction?
I mean, which figure?
The last figure, yeah.
Yeah, this figure, right?
Yeah.
This Y is that Y. This Y is the Y in the left figure.
Yeah.
There's a position of the wind.
So I will start from this figure to talk about this figure then. So in this figure, we can see, for example, at each location there is a wind speed u. depending on the coordinate x and y. So if we express this wind speed as u as a function of x and y, and if we fix x, say this 0d corresponding to x equals to 0 meter. So if we fix x, then the velocity u becomes a function of just y, right? Then this figure shows, this subfigure shows the change of velocity u against the coordinate y. Yeah, it is just confusing because of like in wind turbine aerodynamics, people plotting profiles usually in exchange they reverse the input, so the depending variable and the flow quantities. Yeah.
I also have some general questions. So you have done all these comparisons for wind speeds up to 12 meters per second, or you have also go to high wind speeds?
And for a free stream single turbine flow field, we go up to higher wind speed until 24 meters per second.
Okay.
Then for this wind farm, because we are doing this realistic simulation, so everything is considered, including the atmosphere bounded there and also the operating condition of turbine. So it's
but you have checked it during normal operation. What about gust situations where you have extreme
extreme low?
Can it also?
I think it can be captured because it works fine for the single turbine cases. So I think gust won't be a problem.
Okay.
But if you are talking about extreme events such as hurricane or storm, that probably will be different. Yeah.
And I can see that you have made this test on partially operating case where one turbine was stopped somewhere in the wind farm.
Yeah.
It is on the first row or?
This one.
Yeah, I don't understand how it is first row or not, or how. It's in the front of the others, or?
It's behind the first one. The wind comes from here.
What about maybe try to also have the same case where in the first row you run curtail turbines? You curtail the turbines.
Curtail the turbines for
the first row and how it's impacting the flow
for the rest of them.
Yeah, because you are doing you change the aerodynamics, the flow around the turbine.
Yeah, if you mean just to curtail the first row.
Yeah.
Then the rest are left operating in normal conditions.
Yeah, but
then
it will change.
Yeah, it will change, but the results will be say then the second row turbine will be operating in free stream. Right?
In what?
The second row here will operate in wind conditions similar as in free stream.
Yeah.
Because now these turbines are not working.
Yeah, but not they are working, but they are curtailed.
So they are in a stop.
They start pitching, and so the turbulence can also change.
Yeah, but that will be minor, I think, to the whole aerodynamic, because if the turbine is not rotating, then
it is rotating.
It is rotating.
Yeah, it is rotating. You just
you mean reduce the speed?
Yes, you change the pitch angles.
Yeah.
So you.
Okay, I see. I thought curtailment means the turbine solve to avoid the structural. So it's still working.
It is working.
Yeah. That's another case scenario. Very interesting. Then. Yeah. Thank you. Yeah.
How many LiDAR do you use?
Each turbine have one turbine mounted LiDAR, and we just tested with numerical simulation because actually we try to do as soon as possible with real-world campaign. But we found out that most of LiDAR data campaign now in real-world wind farms, they only rent LiDAR for a certain time of period. And that's why this LiDAR is based on I don't know if you may heard of a ZX LiDAR. And this LiDAR configuration, the resolution, everything is designed based on their LiDAR. It's not from their LiDAR, but we try to be, we're trying to make sure that the LiDAR configuration is as commercially viable as possible. And each turbine has one turbine mounted LiDAR, and it's scanning. Yeah.
Just a follow-up question.
Yeah.
Is it possible you reduce the amount of LiDAR and use physical form? For example, instead of having 3 LiDAR on the first row, you use only 2 and guess the middle one using the physical informed artificial intelligence. I'm not sure how expensive LiDAR is.
It's currently quite expensive.
Because you know the physics of it. Is it possible to predict the middle one based on?
So you mean, for example, for this test case, we mounted LiDAR for the first row and last row, and leaving the middle row.
Yes, and then guess.
Then you will still get a flow field, but and also probably you get a nice result for the effectiveness, but definitely you won't get the meandering effect here, because you say theoretically in this framework you can only have inflow information, then you rely on physics for everything else. But in reality, we want to know.
The LiDAR can also break. The LiDARs can also.
Yeah. The LiDAR, if one LiDAR breaks, then it's fine. But if you really are minimizing the cost by just doing this LiDAR and just leave all of them without LiDAR, then the results will be you're essentially capturing the mean flow structure and the mean wake without the real-time correspondence of the mean. Because it is very chaotic. So you can say it's a deterministic problem because it's governed by a deterministic equation. But still, the problem itself is chaotic. So if without any data-informed information, if without any data into the network, then you won't know the real-time behavior of the wake. You can only know the roughly.
If there is no LiDAR, why search a weak model to simulate, the data from the LiDAr?
I mean,
a weak model to, for example, if there is no LiDAR in the last turbine, maybe we can urge a weak model there to simulate, to obtain the data.
For
Yeah.
yeah.
We will have plenty of time to discuss later on. We have one more question over there.
Yes, thank you for a very interesting presentation. There's obviously a reason why you would do this type of control, right? Because you would like to get out more energy.
Yeah, sure.
Yes, so that is, so you now showed that you can model, you can predict, you have the ground truth. You showed 2 different operations. Which one would you recommend? What type of yaw control or pitch control would you recommend, and how much power do you get extra if you do the proper control?
I see. Thank you. Then I think the main control here, the 2 cases is one is a grid case and one is a yaw control case. And we've already seen some field tests of yaw control, which reported quite different ranges of power gain, from something around 1%, 2% to over 10% power gain by switching from gradient farm to yaw control. So it's hard to say in real world scenario what will be the real gain, because different parties doing research reported such a wide range of power gain, making people thinking about it's hard to know for real world farms. And this digital twin can provide I will claim one more thing, is that it's difficult to say why. I think people reported such wide range of power gain for yaw control is that the wind farm they are applying their control systems are for different wind farms, and that wind farm has a specific layout, and also the distance between the wind turbines also has a great impact. So, for example, in the extreme case, if you have a wind farm that 2 wind turbines are located really far from each other, then you won't bother to do any other control, just gradient control, because there's no much wake interaction. But in reality, wind farms the wind turbines inside the wind farm are located nearby each other. The distance can be 5 5 rotor diameter or 10 rotor diameter, most of them maybe 10 rotor diameter. So that also affects the results. And with this digital twin, what we can provide is that we can, if you run field tests, the data will be very noisy. At some time, maybe your control performs worse. At other time, it performs better. Then overall, over a whole year, the performance gain is, for example, 3%. Then how to interpret that? If we have the flow field, we can then interpret at a certain moment that the wake steering is working. At other moments, the wake steering, for example, if the wind direction is wrongly predicted, then the wake steering may be worse. So with this support of this digital twin, we can make better decisions, at least to do yaw control if the wake is clear away from the downstream turbine, and switch to screen control if such benefit is not obvious. I think that answer your question. Thank you.
Do you have more?
Yeah. And switch to the first.
就是你对着这儿，师兄，你对着那儿就有点那啥，你对着那儿不能对着屏幕，因为你换上下页的时候对这儿就会好一点。对对。
Yeah, so the second part will be the AI-based wind farm modeling. So we've already discussed some effects of wake. This photo shows clearly the wake's impact. So the wakes generated by the front turbines are impacting the following rows. And this wake region is characterized by a reduced wind speed and also increased turbulence level. Therefore, the downstream turbine operating in the wake conditions have reduced power generation and also increased structural load. And in modeling the wakes, we are actually interested in understanding and predicting the wake interactions between wind turbines to support the design of wind farms and also the control of wind farms. And the two main tools for modeling is safety models, which is very accurate, but they are computationally expensive. This is a linear simulation we run at Warwick. For this kind of simulation, the resolution is down to 3 meters to resolve the plate-generated flow structures, and the domain is 3 kilometers times 3 kilometers times 1 kilometers. It's a very large domain to capture the atmospheric boundary layer conditions. And therefore, it requires, for example, in this case, to obtain these results, you require at the local clusters at Warwick, 256 CPU cores and running non-stop for 2 days. So analytical wake model is still very popular because it can be evaluated in real time. And this is a kind of typical result of a static wake behavior. And just a static behavior in the near wake and slowly expanded to the free stream without any detailed structures or dynamics. And in this part, we aim to develop AI-based model that can be evaluated in real time, similar as analytical wake models, but at the same time capturing high fidelity flow features. And also it requires to be generalized while to unseen flow scenarios, and also it can be scalable to larger wind farms. And in this field of works, we considered both the static wake models and the dynamic wake models. The overall framework is to run a set of larger simulations, CFD simulations, to generate a high fidelity database. Then based on this database, we design and adapt cutting-edge machine learning models to learn from the data about the flow dynamics. Then after training, it can be used as a fast simulator for the wind farm wakes. And for static models, we begin with dimensionality reduction to extract a low-dimensional feature of the flow field, then building machine learning models to predict such feature, then reconstruct back to the whole flow field. And this introduces the dimensionality reduction error, and we further developed a approach that arises from image processing problem to avoid this procedure. So basically, this problem for static modeling, we can easily draw the analog between this task with image processing, because basically if we consider the average flow field is just a multi-channel image in computer science. And we then further developed a framework called multi-fidelity model, a super fidelity network. The idea is to incorporate both high fidelity data and low fidelity data, such as generated by analytical models. So this kind of data blending idea is also maybe useful to other ESRs working on other fields, because quite often in many fields that high fidelity model and middle fidelity or low fidelity model all exist. And by blending these models of different fidelity, we are able to reduce the need of generating a lot of high fidelity simulation data, which is very expensive, therefore reducing cost of building such machine learning models. And for the dynamic weight modeling part, the first part following the same idea, but we need to more dedicated design of sequential prediction problems. And the latest work based on a newly designed framework, neural network structure called bilateral convolutional neural network, which basically to incorporate in the neural network structure about the basic understanding of the flow field, therefore avoiding this dimensionality reduction process while retaining a robust performance of iteratively predicting the future flow field. And this is an overview of the high fidelity database generation. So I mentioned that each case requires 2 days simulation, and for this case we are able to generate 60 cases, which roughly requires this amount of CPU hours. So this reflects really expensive to prepare such database. And the simulation begins with atmospheric boundary simulation, which is a simulation of the atmospheric conditions. Then using this simulation, we can extract the boundary conditions for the inflow and also as initial conditions for the wind farm to operate. Then the wind farm simulations are carried out with each wind farm consisting of 3 cells operating in a row under these atmospheric boundary conditions. And we can see an instantaneous flow field view here at half height. So the machine learning model, the target is now, instead of using machine learning model to predict the whole flow field, we predict the flow field surrounding each particular turbine with input as the turbine operating conditions and also the flow quantities at the subdomain boundary. So with this kind of approach, after training, the machine learning model can predict the flow field from one distributed wind turbine structure. And for the whole farm, then we can do this sequentially from upstream and extend the prediction to the whole farm. And this is results for the static weight prediction. This shows the single turbine case. This is the multiple turbine case. And we can now see the static weight behaviors. This is the machine learning prediction based on image processing machine learning model called GAN. And this is the results obtained by the CFD simulations. We can clearly see feature captured, such as the wave propagation direction due to the yaw angle of the turbines. And this is for the streamwise velocity, and this is for the crosswind velocity. So we can clearly see that the crosswind velocity induced by the turbine yaw angles is also captured in this case. And for, as I mentioned earlier, that for the static wind turbine wave behavior, we can clearly see the double peak structures slowly evolve into the Gaussian shape. That's why from last century, 1980s, people start working on the modeling, analytical modeling of waves, usually consider this Gaussian shape modeling approach. And this is, after training, we tested with 2 cases. This is a case of 6 turbines with graded case. This is the optimized yaw angle case. And again, we can see is the streamwise velocity, this is spanwise, so the crosswind velocity. And we can see the prediction for both velocity components is accurately simulated by the machine learning model. And more interesting is the dynamic weight prediction. And this is a turbine operating in free streaming flow. This is the result of a turbine operating in a weak inflow. So there is a turbine operating in the upstream. And this is the CFD simulation results. This is the machine learning prediction. So we can see the propagation of the structures. The weak regions are all predicted quite nicely. And finally, the final demonstration is for test wind farm. We can see the propagation of the weak structures and also some meandering effects. And for this kind of simulation of a whole wind farm, if we want to capture these kind of features using traditional approach, it would take at least several days or several weeks on supercomputers. But this can be done on a laptop within several seconds to just quickly have a view of this dynamic flow field. So this is the modeling part. Any questions?
Okay, but thank you very much.
Thank you.
Obviously, we all need a short break.